Good day, ladies and gentlemen. Today we enter the last two sections of Chapter 10, or the last two parts at least. We will be comparing two means. We'll be doing two sample tests for means. We'll be looking at confidence intervals. We'll be looking at significance testing. So here we go. Here are our learning objectives for today. This is what you should be able to do upon completion of both of these videos. So in the last two videos, we developed methods for comparing two proportions. We found the difference of them. We've calculated probabilities. We looked at describing the distributions. We found confidence intervals, and we did significance testing. But what if we want to compare the mean? And I bet you saw this coming based off of the last several chapters. We did proportions and then means, proportions and means, proportions and means, and that's what we've been doing. So if our parameters of interest have mean 1, mean 2, mu1, mu2, the best approach is, again, to take separate random samples from each population and compare those sample means. Suppose we want to compare the average effectiveness of two treatments in a completely randomized experiment. In this case, mu1 and mu2 are the true mean responses for the two treatments, and we use the mean response in the two groups to make the comparison. So we have two populations or treatments. We are wondering about the true parameters of the mean. We collect the sample mean of each from a sample size of N1 and N2. This should be nothing new. In Chapter 7, sampling distributions, we have shape, center, spread. SOX, we don't really deal with the outliers in this, but we could talk about it. The shape, it's approximately normal, or if the population was normal, or if we satisfy the central limit theorem, that is n is greater than or equal to 30. The center of our distribution will be mu sub x bar, and the spread will be sigma divided by square root of n, provided that our 10% condition is met. We're going to look at a sampling distribution between two means, and we're going to look at data from the National Health and Nutrition Examination Survey regarding the heights of 10-year-old girls. And what we find is that those follow a normal distribution with a mean and standard deviation here. The heights of 10-year-old boys also follows a normal distribution with mean and standard deviation here. So let's suppose we take simple random samples of 12 girls and 8 boys, and we measure their heights. What can we say about the difference between the mean height of females and the mean height of males? So here is a sampling distribution of our females, our sampling distribution of our males, and we see that those are both normal. We have our centers, which are 56.4, 55.7. If I go back here, that's what the means were. We can calculate our spread, 0.78, 1.34, and this is a sampling distribution of the differences. And notice the shape is still approximately normal. The center can be found by taking the mean of the females minus the males, this minus that. And the spread, hope you saw this coming from the last section, the spread, guys, is the sum of the variances of the two samples. Because we're subtracting two random variables, the means get subtracted, but to calculate the new standard deviation, or variance for that matter, we need to add the two variances before, not the standard deviations. Therefore, the mean of our sampling distribution, x bar 1 minus x bar 2, is the difference of the two population means. Our standard deviation of our new sampling distribution will be the square root of sigma 1 squared over n1 plus sigma 2 squared over n2. This is a typo right here, ladies and gents. Please make note of that. This should be sigma 2 squared, as should this. So here's a summary of that. Again, we can only use normal calculations when the shape of the population distributions are normal, or our sample sizes are large enough, that is, we satisfy the central limit theorem. Our center will be mu1 minus mu2. And what that means, to use some statistics terminology, is that the difference in sample means is an unbiased estimator of the difference in population means. And our standard deviation can be calculated as such, provided that our 10% condition is met. So here's a picture of that. Should look familiar. A little bit different formulas though, guys. Let us calculate some information here. So we're going to take this information about the boys' and the girls' heights. We're going to describe the shape, center, and spread. So because both populations are normal, we know the sampling distribution of x bar sub f minus x bar sub m must be normal. Its mean will be mu sub f minus mu sub m, which is 0.7 inches. Its standard deviation will be found using the formula, and we get 1.55 inches. And if I want to find the probability of getting a difference in sample means that is less than 0, we're looking at a bell curve like so, and we're finding a z-score of negative 0.45. This is where the difference is equal to 0. This is our z-score. If I go back to this picture, here's xf minus xm equals 0. Standardizing it, we get this picture. And we can use table A, or we can use our graphing calculator and find that the area is 0.3264. So does this give reason to doubt the researchers' stated results? If the mean height is greater than that of females, that is, if xf minus xm is less than 0, part B is showing that there's a 33% chance of getting this difference that's negative just due to sampling variability. It's not that unlikely to happen. So this gives us little reason to doubt the researchers' claim. Okay, t-statistics, confidence intervals. Here we go. So when data come from two random samples, the statistic x bar 1 minus x bar 2 is our best guess for the value of mu1 minus mu2. Because a lot of times we don't know the population value. We've been studying that. When the independent condition is met, our standard deviation of this statistic is as shown. But we don't know the parameters sigma 1 and sigma 2, so we use the standard deviations of the samples, S1 and S2, and now we're talking about the standard error, not the standard deviation of this new sampling distribution. If the normalized condition is met, we can standardize the observed difference to obtain a t-statistic that tells us how far the observed differences is from its mean and standard deviation units. So again, we're going to be finding t because we don't know sigma and we're using the standard error. So here is the t formula, difference of the x's minus difference of the means over the formula for standard error. The two-sample t-statistic has approximately a t-distribution. The easiest way to deal with this is to use technology to determine the degrees of freedom and do our calculations, or we can use what's called a conservative approach, using the smaller of n-1 and n-2 for the degrees of freedom. So the conservative approach, if there were 12 in this group, and 8 in this group, we're going to use the smaller of the two numbers, so we would use 7 as the degrees of freedom. The technology does a much better job, and it's actually way tons easier to make these calculations. We're not going to have to approximate nearly as much. So my suggestion is using tech. So here is a nice, succinct summary. Get this in your notes. Okay, example. Here we go. We're talking trees, small trees, big trees, short trees, tall trees. Say that 10 times fast. I bet you get lost in the forest as it is. So we have a preserve in Georgia. It's an old growth forest. It has lots of pine trees, and they survived for hundreds of years. We're wondering, how do the sizes in the north part of the forest compare to the south part of the forest? Why wouldn't we care? It's the kind of thing that a lot of naturalists do study. So we have box plots for the two sets of data here, and we have the data, the summary statistics for a sample of 30 trees from each part of the forest. We're going to construct and interpret a 90% confidence interval without technology. We'll use the technology in a minute. So we're going to state what we're doing. Our parameters, we need to define them, mu1 and mu2. Mu1 is the true mean for the diameter at breast height in centimeters of all trees in the southern half. Mu2 is the true mean dBH of all trees in the north half. We want to estimate the difference, mu1 minus mu2, at a 90% confidence interval. Plan, we're going to use a 2-sample t-interval if the conditions are satisfied. So in our plan, did they come from random samples? You betcha. Normal. Well, the box plots give us reason to believe that the populations might not be normal. If we go back and look at those, they're not. I mean, you look at the south, that's not normal. That's skewed to the left, and the north is skewed to the right slightly. But guess what, guys? Remember, since both sample sizes are 30, we are safe using our procedures. We satisfy the central limit theorem. Independent. Researchers took independent samples from the north and south. Because sampling without replacement was used, we have to check our 10% condition. So it's safe to assume that there are at least 300 trees in each half of the forest. This is a big forest, guys. So our conditions are met, and we're going to use the conservative degrees of freedom of 29. So we're taking our sample size 30, subtracting 1, and since it's both sample sizes are 30, we don't have to pick which one is smaller. So degrees of freedom 29. So we use our table. Our upper tail probability will be 0.05. Remember, we have to split that in half. We're doing a 90% confidence interval. Our upper tail would be 5%, not 10%. Degrees of freedom is 29. So our t-score is 1.699. And we can then calculate our confidence interval, difference in the x-bars, plus minus t times standard deviation, standard error, and we get this confidence interval right here. And what does it mean? Well, we're 90% confident that the interval from 3.8 to 17.83 centimeters captures the difference in the actual mean dBH of the southern trees and the actual dBH of northern trees. This interval suggests that the mean diameter is between 3.83 and 17.83 centimeters larger than the mean diameter of the northern trees. Whew! Okay. In the second video, we're going to look at doing significance tests for mu1 minus mu2. And in here, I'm going to revisit how to use our TI Inspire to calculate these values from some sample statistics. So that is all. I shall see you in part 2.